Assalamualaikum and hi, we are from AS1205M and we will present about the case study of gas chromatography and high performance liquid chromatography. Gas chromatography is an analytical method that separates chemical components in a mixture. The sample used is either gas or liquid that is vaporized in the injection part. The mobile phase is the carrier gas. Then the sample is transported into the column by carrier gas, either hydrogen, nitrogen, helium or argon to be separated. Helium and argon are preferred because of low molecular weight and chemically inert. Then the components pass through the detector and electrical signal is the result of the detector. Gas chromatography is widely used in most industries for quality control or manufactures of many products such as cars, chemicals and pharmaceuticals for research purposes and safety from the environmental. Also used in quantitative and qualitative analysis.
For sample preparation gas chromatography, dichloromethanes was used to stabilize the aroma compound. Each vanilla was placed in an aluminium flask with saturated solution. The solution was placed on a magnetic stirrer. The mixture was separated in a separating funnel to examine the compound. Headspace soft extraction was used to extract sample. A few silica capillary column was utilized to separate vanilla sense component. The temperature of the gas chromatography oven was set to 35 degrees Celsius and heated up with mass selective operated at 70 electron volt. A capillary gas chromatography column was linked to an uncoated transfer line. The transfer line was heated up and mixed with humidified air to prevent dryness. The quantification finding of the vanillin component were done by comparing the peak area of the aroma compound to the peak area of the chosen internal standard.
SO analysis. GCMS analysis were done firstly for poor vanilla extract and secondly, the same extracts were analyzed by GCMSO technique. This technique resulted in order description by highly trained sensory scientists. GCMS analysis of vanilla extract. However, from the sensory result, the extract with the highest score for the powdery fruit note was found for the PNG extract, whereas the Madagascan and inundation extract did not display the sensory characteristic. The level of vanillin was similar for all three extracts, whereas the sensory evaluate shows that Indonesian extract had less powdery vanilla than other extract. The result was correlated with the sensory result, showing that anesthetic and almond descriptors had the highest score for the same extract. Ethylbutanoate and ethylhexanoate have the highest levels among the ethyl ester found mainly in Indonesian extract. Anesthetic found in PNG extract contribute to enhancing of powdered vanilla. The sensory results show that the Indonesian extract as well as the Madagascan one had a high score for Rami descriptor. The powdery fruity notes in PNG extract are explained by the high level of anesthetic acetane. These two aroma compounds are correlated with the woody and phenolic descriptors that were identified with a higher score in the sensory evaluation for the Madagascan origin. The level of violation acid was highest in the Indonesian vanilla extract. It is clear that the V. tahitensis extract, which originated from PNG, contains the highest amount of anisaldehyde and anisyl alcohol. GCMS analysis were done firstly for poor vanilla extract and secondly, the same extracts were analyzed by GCMSO technique. This technique resulted in order description by highly trained sensory scientists. GCMS analysis of vanilla extract. However, from the sensory result, the extract with the highest score for the powdery fruit note was found for the PNG extract, whereas the Madagascan and inundation extract did not display the sensory characteristic. The level of vanillin was similar for all three extracts, whereas the sensory evaluate shows that Indonesian extract had less powdery vanilla than other extract. The result was correlated with the sensory result, showing that anesthetic and almond descriptors had the highest score for the same extract. Ethylbutanoate and ethylhexanoate have the highest levels among the ethyl ester found mainly in Indonesian extract. anisole found in PNG extract contribute to enhancing of powder vanilla. The sensory results show that the Indonesian extract as well as the Madagascar one had a high score for Rami descriptor. The powdery fruity notes in PNG extract are explained by the high level of anisole acetane. These two aroma compounds are correlated with the woody and vanillic descriptors that were identified with a higher score in the sensory evaluation for the Madagascar origin. The level of violation acid was highest in the Indonesian vanilla extract. It is clear that the V. tahitensis extract, which originated from PNG, contains the highest amount of anisaldehyde and anisyl alcohol. Both analytical methods such as QDA with train panels and with CHM260 analysis show that there is a clear relationship between sensory characteristics of three different origins of poor vanilla extract and their sensory characteristics in white and in milk chocolate. For Indonesian vanilla extract, the panel found that white chocolate had a more intense milk powder attribute, whereas the milk chocolate had more intense buttery notes. This aroma compound related to fruity note, respectively fermented note together with glycol and vanillin are the key aroma compounds in Indonesian vanilla. There are two aroma compounds with spicy notes together with glycol and vanillin are the key aroma compounds in PNG vanilla. In conclusion, we may assume that replacing V. tahitensis vanilla extract by V. planifolia could impact the sensory profile of the chocolate, but this effect would be minimized if the cocoa content was relatively high, such as in a dark standard chocolate recipe.
By gas chromatography method, the sensory QDA profile of PNG samples differs from that of the Madagascar and Indonesian samples. Within the chocolate base, plant vanilla varieties of an origin have a greater influence on their sensory profile than their origin. GCMSO results correlate with the sensory properties of both vanilla extract and chocolate samples. TDS analysis confirms that sensory perception is strongly influenced by cocoa content. The higher the number of cocoa solids in the chocolate, the lower the perception of vanilla, especially among untrained consumers. On average, consumers do not identify which chocolate is much more preferred, except from the Belgian group. Certain chocolates may appeal to some people more than others. However, it is influenced by a variety of factors, including nationality, gender, age, and product participation. There are three limitations in the current research. To begin with, the vanilla doses in white and milk chocolates were determined experimentally. Future research should look into how adjusting the vanilla concentration in chocolate affects flavor perception. Next, because to the small number of participants in each of the 4 countries, only indicative sensory preference may be drawn. In future studies, it is suggested that the sample size be increased. Finally, by using identical sensory descriptors, sensory and non-sensory research methodologies should be better integrated. For instance, untrained consumers and trained panelists may interpret Rami and anisole qualities differently. In conclusion, the objective of this experiment has been achieved, which is to find out to what extent the vanilla growing in one country can be replaced by vanilla growing in another country.
High-performance liquid chromatography, or Hplc, is also an analytical method in which the sample is automated pumped in the mobile phase at high pressure through the stationary phase. Hplc mobile phase is in liquid. Consists of separation, identification, and quantification of components in a mixture. The sample is automated injected and travel through the column by carrier gas with the chromatographic packing material called as stationary phase. The carrier gas is either helium or nitrogen. The components in the sample are separated and its retention time will vary by their different degree of interaction between the stationary phase. Retention time is the time taken for a compound to travel through the column to the detector, and different compounds have different retention time. When the sample passes through the column, it will interact between two phases, which are normal phase and reverse phase, at different rate because of the different polarity in the analytes. And the last part is the detector. The results in the detector are known as chromatograph. Hplc is extremely sensitive and highly automated.
Sample preparation for Hplc method is 1.5 kg vanilla sample were cured through hot water scalding, dry in the oven in the sun, and fermented it, then dried again in the wind to decrease water content. For pre-extraction 1, 200 ml ethanol was used to extract pure vanilla, then transferred to 250 ml volumetric flask. The flask for extraction was rinsed with ethanol, then poured to volumetric flask. Add the ethanol until the mark and mix well. For pre-extraction 2, 10 gram pure vanilla was submerged into ethanol. Then using filter paper, transfer the ethanol to 250 ml volumetric flask. The submerged pure vanilla was pounded using mortar. Repeat step 1 until 3. Then pure vanilla was rinsed with ethanol, transferred to volumetric flask. Then add the ethanol till mark and mix well. For Hplc, it combined with UV spectrometry. Using 10 ml methanol, 90 ml acidified water, vanillin was separated on reverse phase column and detected at 280 nanometer. The Hplc flow rate is 4 ml per minute. After that, the quantification of vanillin content was analyzed using following formula.
On this slide, we will talk about the Hplc method that has been used for the separation of vanillin in food and essential oils. So the Hplc method for separation vanillin in food and essential oils use a column of 150 mm length and 4.6 mm ID with 5 micrometer packing L7. For a direct comparison, we applied the Hplc method using a variant pursuit XRS C8 5 micrometer and 150 times 4.6 millimeter column. And the sample concentration is about 0.48 milligram per milliliter, and the column is pursuit XRS C8 5 micrometer, 150 times 4.6 millimeter, and the last one, injection volume, is 5 microliter. The next one, the resolution between the phenolic aldehyde internal standard IS and vanillin must be greater than 1.5, and the tailing factor, measure of peak symmetry, must be less than 2.0 for these peaks according to the Hplc method. The performance of the Pursuit XRS C8 5 micrometer 150 times 4.6 millimeter column much exceeded the standards indicated in the Hplc method. And the last one, the retention times, on the other hand, necessitate 15 minutes run times, which can reduce sample throughout the productivity. Next, to boost productivity, a shorter column with the same bonded phase but lower particle size, the variant Pursuit XRS C8 3 meter 50 times 4.6 millimeter was used. The same chromatography conditions were utilized, with the exception that the injection volume was reduced to 3 liter to account for the decrease in overall column volume. The next one, the results obtained exceed the requirements of the Hplc technique. However, the run times can be lowered to less than 5 minutes. Next, the sample concentration was about 0.48 milligram per milliliter. The column is Pursuit XRS C8 3 micrometer 50 times 4.6 millimeter, and the injection volume is 3 microliter. Next, for both retention time and area, the Hplc method for this separation stipulates a required level of precision. The relative standard deviation for replicate injections should be less than 2.0% for an acceptable analysis. And then the linearity test for standard solutions was also performed using 5 standard solutions, which are 50%, 70%, 100%, 125%, and the last one is 150%. And lastly, as a result, the Hplc methods can be used to measure vanillin in a linear range of 50 to 150% of the standard level.
Using high-performance liquid chromatography method, there is higher vanillin content in the pre-extraction treatment for cured vanilla because of the perfect direct contact between vanillin component in vanilla sample and extraction solvent. The succination extraction produced higher vanillin content than the prosylation extraction because of the succination extraction that contains continually solvent purity process. Therefore, there is high density of the vanillin content in vanilla extract. Next, in determining the vanillin content of vanilla, because vanillin was separated from other compounds, Hplc method offers a more accurate means than the ISO spectrophotometric assay. In conclusion, the objective of this experiment, which are to analyze vanillin in vanilla extract by Hplc method and to compare the accuracy of the Hplc and spectrophotometric methods in the determination of the vanillin content, have been achieved.
That's all from us. Thank you.